All right, let's unpack this. For years, the ultimate dream for AI music, it felt like this distant symphony, didn't it? We had AI that could, whip up a quick 30-second loop maybe.
Yeah.
Or handle a vocal track separately from the instruments.
Right, they were often treated as totally separate things.
Exactly. But a full, cohesive song with actual lyrics, convincing vocals, complex accompaniment, all just from a text prompt. That was the holy grail. It always felt just out of reach.
Yeah, like trying to teach a machine quantum physics when it was still learning basic arithmetic.
Yeah. And the sheer complexity of that challenge is, well, it's immense. Before what we're diving into today, these open source models, they mostly hit a wall.
Yeah.
Short clips, maybe.
Or they treated singing and instruments as completely different problems. Like you had great engine builders over here and great chassis designers over there, but putting the whole car together reliably at scale, that was the struggle.
And then along comes YuE. Not just, another model, but a whole family of open foundation models built on LMA2 architecture.
Right.
And aiming squarely at this massive lyrics to song problem. We're talking generating pretty high quality music.
Yeah.
Up to 5 minutes long.
Which is a big deal.
Yeah. Complete with lyrical alignment, coherent structure, decent vocal melodies. It's like a big flag planted for open source saying, hey, we can do this too.
And that immediately brings up the big question.
Yeah.
How? How did they manage to string together a whole musical story when others were kind of stuck in these fragmented loops?
Exactly.
So our deep dive today, using the fantastic sources you shared, is all about unpacking the really clever technical tricks you use to make this happen.
Yeah, you send over some great stuff, and we've been digging in, pulling out the key bits, the surprises, and just how you managed to turn this huge challenge into, well, actual music. So get ready for some breakthroughs. Okay, so let's kick things off. A really big hurdle, right, for any AI music generator. It's getting vocals and the backing track, the accompaniment, to work together without one just totally drowning out the other. It sounds a bit like trying to listen to two people talking at once and writing down both things accurately.
Exactly. That's a perfect way to put it. The old way, standard next token prediction. It just couldn't handle what the paper calls these dense mixture signals you get in music.
Right.
They actually call it LAT, linguistic information loss after tokenization. So like in really dense stuff, heavy rock maybe?
Yeah.
The instruments could just completely swamp the vocals. You lose the lyrics.
Oof. Okay, so the lyrics just get lost in the noise.
Yeah.
That's obviously not going to work if you want a lyrics to song model.
Definitely not.
So how did you get around that, this noisy problem?
Well, what they did was build in something called a source separation prior. Basically, instead of one token trying to represent everything at each moment, they went for a dual token strategy. So the model actually spits out two separate tokens. One's just for the vocal, and the other's just for the accompaniment, like giving the AI two separate ears almost.
Two separate ears. I like that. So what were the big wins with this dual NTP approach?
Well, it had a few key advantages. First, it kind of fits neatly into the existing language model architecture, makes it scalable.
Okay.
And testing showed it led to lower training loss. And crucially, robust lyric adherence, even in tricky genres. So the lyrics stayed clear.
Nice.
Plus, it lets you model both tracks together in one go, avoids sync issues, and you get finer control, granular modeling, they call it. You could even process them separately later.
Okay, so dual tracks sorted, but then there's the next massive challenge for making a full song. Coherence, keeping it all together.
Right.
How do you stop the AI just wandering off creatively after 30 seconds. Humans plan songs, right? There's structure.
Exactly. And just making the context window bigger for the language models, that turned out to be non-trivial. A real headache was this long-term decay thing with positional embeddings, like rope.
Rope. Remind me quickly. Rotary positional embeddings. It's basically how the model keeps track of word order and position over long stretches. But the problem was, any instructions you gave at the start, like the lyrics, they'd start to fade, degrade after about 6,000 tokens.
Yeah.
Which, in a song several minutes long, means, well, total failure. Lyrics forgotten, structure gone.
Yikes. So it's like the AI has this great opening line, but forgets the whole point by the second verse. Sounds like a research nightmare.
Pretty much.
So how did you give the AI a better memory, for the whole song structure?
They brought in something called structural progressive conditioning. They call it YuE, inspired by chain of thought prompting.
Oh, okay.
And they leaned into the natural structure of music, intros, verses, choruses, bridges, outros.
Building block.
Precisely. They automatically chopped the songs into sections, usually around 14 of them, each under 30 seconds.
Okay, and then what did they do with those chunks? They interleaved structured text and audio tokens within each segment. So the model gets a little signpost at the start of each bit, like intro, then the lyrics for that section, then the audio tokens.
Ah, I see.
It provides these intermediate guideposts, keeping it on track, ensures song-level lyrics following, and structural control over the whole long piece, breaks the big problem down.
All right, so now we've got these full structured songs happening. But what if I want to say, hey, AI, make it sound like this song, a reference-based generation. In context, learning works for speech, but music feels different, harder.
Absolutely. Just taking the standard speech ICL approach and applying it to music, it caused big problems.
Like what?
Well, for one, it often needed the lyrics for the reference track, the text, and you don't always have that for music.
True.
It also kind of assumed you'd always generate linearly, which isn't always how you want to create music. Like maybe you want to build a whole track just from a cool chorus idea.
Right, limits creativity.
Mm-hmm.
And I guess the scary part, from a producer's view, is the model might just copy?
Exactly. It might replicate the reference melody or even entire segments. Big copyright red flags there. Nobody wants an AI parrot.
Definitely not.
Right.
So how did you teach it to be inspired, not just a copier?
They totally redesign in context learning for music. So instead of text, they just stick a 20 to 40-second audio snippet from a reference track right at the beginning of the COT data.
Okay.
And that snippet could be the full mix, or just the vocals, or just the accompaniment. Much more flexible.
But wait, doesn't that bring back the copying problem if you feed it the audio?
Ah, this is the clever part. Their delayed activation strategy for ICL. This is crucial.
Delayed activation.
Yeah. They found in early tests that if they introduced this reference audio, the ICL data, too early in the training, the model learned a shortcut. It just leaned way too heavily on that reference audio. Overfitting happened. The musicality actually went down.
Oh, interesting. It became lazy, essentially.
Kind of. And it was really hard to fix once it learned that bad habit. So YuE only introduces the ICL data right at the end of training, during what's called the annealing phase.
Annealing, like cooling metal slowly.
Exactly like that. It's the final tweaking stage, and it's only about 2% of the total training time.
Wow. Okay, so they make sure it's a competent composer first, build that solid foundation.
Right.
And then they gently teach it how to take stylistic hints without just plagiarizing. That's really smart.
It is. And it allows for this disentangled control, as they say, between the text prompt and the audio reference, lets you do really cool style transfers. They mention turning like Japanese city pop into English rap, but keeping the original backing track.
That's properly creative generation. Now, talking about training, these big models, they need so much data. But finding high-quality, matched lyrics to song data, that sounds incredibly difficult.
Well, it is inherently scarce, as the paper puts it. That's one huge challenge.
And the other?
The other is that large models, they just love to overfit. They latch on to whatever signal is strongest or most common in the training data.
Right. So how did you deal with scarce data and the overfitting risk?
With a really carefully designed multitask, multi-phase, pre-training recipe?
Multitask, multi-phase.
Awesome.
Sounds intense. Break that down for us.
Okay, so multitask means training the model on several related tasks at once, not just the main one. This helps transfer knowledge and makes the model more robust.
What kind of tasks?
They use three main ones. First, text-to-speech, TTS.
Okay, why TTS?
Absolutely essential for getting the lyric following right and just modeling human voices realistically. Without it, they said, lyric control was basically ineffective.
Gotcha.
Though, funnily enough, they found if they overdid the TTS training, the model just wanted to wrap everything.
Okay, what else?
Second, just general music generation, both unconditional, just making music, and tag conditioned. Most of their data, 650,000 hours, was just music. They used another model, Qwen2 Audio, to automatically generate descriptive tags, genre, instruments, mood.
Smart. And crucially, they used UVR, that's an open source separator, to split about 40% of this music into vocal and accompaniment tracks, feeding into that dual token strategy we talked about.
Ah, connecting the dots. And the third task.
That was the main goal, lyrics to song. And this task really benefited from the other two, plus the QT structure for handling noisy lyric data.
Okay, that's the multitask. What about the multi-phase?
That's about the order they did things in. Very carefully sequenced, 4 phases.
Phase 1.
Warm up, just getting the basic capabilities going. Then a constant learning rate phase, where they started adding in some lower quality multilingual data.
Okay.
Then context extension. This is where they gradually stretch the model's attention span, that context length, up to over 16,000 tokens for those long songs.
Makes sense. And the final phase?
Annealing with control injection. This is the crucial bit we touched on with ICO. They actually removed the speech and unconditional music data here.
Oh, interesting. And carefully introduced the stronger control signals, like that delayed ICL. This whole careful sequencing stopped the big models from getting stuck with overly generic priors. They actually called this problem catastrophic inertia in earlier attempts that didn't work.
Catastrophic inertia.
Yeah.
Sounds bad. So this careful dance of tasks and phases was key. So let's peek under the hood a bit. What are the actual building blocks here? What kind of architecture did you use, especially for understanding the raw sound?
Okay, so fundamentally, YuE is an autoregressive language model framework. Think LaMA2 based. It works in 2 stages.
2 stages.
Yeah. Stage 1 is the music language modeling, or MULAM. That's built on LaMA2, and it handles the big picture, the semantic meaning. It uses these special codebook-audio tokens that are rich in meaning.
Codebook-0, okay. And stage 2?
Stage 2 is residual modeling. It's actually a smaller LaMA2 model that comes in after stage 1. It adds the finer details using the other codebooks from the tokenizer to refine the audio quality.
Got it. And that audio tokenizer itself, the thing turning sound into tokens.
Yeah.
You mentioned that was a tricky part for music AI.
Oh, absolutely. A major learning curve for them. They found that the purely acoustic tokenizers, things like encodec or hyphacodec, which are popular in speech, they just failed to converge efficiently on the messy, diverse music data. The models struggled to learn. Outputs were often just noise or silence.
Why was that?
Because those tokenizers are mainly built for compression, getting the file size down. They don't really prioritize capturing the musical meaning, the semantics.
So focusing too much on the raw sound details actually made it harder for the AI to understand the music.
Exactly. It's a bit counterintuitive, but yeah. In contrast, what they call semantic acoustic fused tokenizers, ones that blend both meaning and sound information, they worked much better.
And which one did you end up using?
They went with Xcodec. They specifically noted that its codebook dash alone captures rich semantic information like melody and vocals. That choice was really critical for making the training work on real-world, in-the-wild music data.
Okay, the tech sounds impressive. Very clever solutions. But, you know, the proof is in the pudding. How did you actually sound? How did it stack up against the big names, the proprietary models like Suno, Udio?
Right, the evaluations. So they did human evaluations back in January 2025, and the results were pretty encouraging for an open source model.
Yeah.
It clearly outperformed another model called Hilo, and it achieved comparable results to Tiangong and Udio.
Comparable to Udio? That's significant.
It is. Now, it still trails behind Suno V4, which they acknowledge is kind of the state of the art right now. But still, getting into that competitive range as an open source project is a big step.
Definitely. So it wasn't quite top of the pack, but punching well above its weight. Where did it really do well in those tests?
It really shone in music structure and music arrangement. That makes sense, given the QD approach for coherence.
Sure.
Also scored strongly on genre adherence, instrument vocal consistency, and emotion control.
And the weaknesses, where did it fall short?
The main areas flagged were vocal and accompaniment acoustic quality. The actual sound wasn't quite as polished. The researchers think that's likely down to the audio tokenizer they're using currently. Maybe room for improvement there.
Okay.
And it was more moderate on controlling specific emotion and tempo.
Were there any, surprise metrics? Anything unexpected that stood out?
Yeah, actually. This vocal agility metric. Turns out you had one of the widest vocal ranges, about 27 semitones on average, which was right up there with Suno V4.
Wow.
But the really fascinating bit was that this vocal range score had a super high correlation over 0.85 with people's subjective ratings of musicality and overall preference.
No way. So how wide the vocal ranges could actually be a good proxy for how good the AI music sounds overall?
Seems like it, yeah. A potential aha moment for evaluating these things objectively.
That's really interesting. And just to confirm, it really does make long songs, not just clips.
Oh, yes. Critically, YuE produces the longest audio with a much wider range of durations than the others. It really delivers on that promise of full-length song generation.
Okay, now this is where things get, really cool for me. Beyond just doing its main job well, Did scaling up YuE lead to any weird, unexpected abilities? Emergent stuff?
It absolutely did. As they scaled the models, they saw several novel abilities just pop up, things they didn't explicitly train for.
Like, give me examples.
Okay, get this. It started spontaneously using advanced vocal techniques, vibrato, glissando, bel canto, but also things like death growl.
Death growl. From Lam A2, that's wild.
Isn't it? And even things like Beijing opera singing style, Shanbui folk vocals just emerged from the data.
Incredible. What else?
It showed spontaneous performance behaviors. Like if it ran out of lyrics in a jazz piece, it might just start scat singing.
Seriously?
Yeah.
It improvised.
Seems like it. Or producing complex multi-part harmonies in a cappella styles, or even adding little instrumental solos, like a harmonica break appearing during a pause in a folk song, totally unprompted but fitting the context.
Wow. That's not a generation. That feels like performance intelligence almost.
It blurs the lines, doesn't it? And then there's the cultural stuff.
Yeah.
It got really good at world music and pattern mixing. They gave an example of creating Chinese gangsta rap accompanied by Japanese shamisen.
That's a fusion I haven't heard.
Right. It also showed high-fidelity voice cloning, mimicking singers like Billie Eilish or Faye Wong pretty well, and really versatile style transfer. Remember that Japanese J-pop to English rap example?
Yeah.
Plus, it could handle code switching naturally, flipping between languages within the same song's vocals.
Amazing stuff. But as always, it wasn't just smooth sailing and cool emergent abilities. The researchers were good about sharing the dead ends, too, the unsuccessful attempts. What were the big lessons learned the hard way?
Yeah, they highlighted 3 key things that just didn't work. First, trying to train these big models only on those raw acoustic tokens.
The ones focused on compression.
Exactly. It consistently led to convergence difficulties, higher losses. The models just struggled to learn. Outputs were often noise or silence. The tokens didn't carry enough musical meaning, so the models took shortcuts that didn't lead anywhere useful.
So trying to feed it too much raw sound detail actually backfired.
Yeah.
Got it. What was number 2?
Unconditional pre-training for the really large models, like their 7 billion parameter one, actually became counterproductive.
Oh, so?
The big model learned so much general stuff about music from the huge unconditional data set that it developed these overly generic priors.
Yeah.
And those general patterns kind of overshadowed the specific instructions needed for the lyrics to song task. The model got stuck that catastrophic inertia they mentioned. It couldn't adapt properly.
So it learned too much general knowledge and couldn't focus on the specific job.
Precisely. And the third big lesson.
Let me guess. The in-context learning timing.
You got it. Early activation of ICL data led to poor musicality. Doing it too soon absolutely caused that overfitting, that shortcut learning where it just copied the reference. And it was really hard to undo that damage. It directly proved why their final delayed activation strategy was so important. So if you sort of zoom out and look at the bigger picture here, you really feels like a significant moment for open source AI music. It's not just about making tunes. It's pushing what these models can grasp about something as complex and structured as a full song with lyrics.
Yeah, it's pretty credible. They really seem to crack several key problems at once. Getting the vocals and music balanced, maintaining that long-term coherence with the Cao-Ti method, and figuring out how to use reference audio creatively without just copying it. And then you get these wild emergent things like scatting and death growls. It really shows how much smart design choices in the architecture and the training process matter.
Absolutely. And it raises a fascinating question, especially for you listening. As these AI models, like you, get better and better at understanding, replicating, and even blending diverse musical styles from around the world, how might that change music itself? Particularly thinking about those underrepresented musical traditions the researchers hope to support with open source tools like this.
Yeah.
What does it mean when AI can learn and potentially evolve those styles?
That is a great question to ponder. Food for thought.
Yeah.
And that brings us to the end of our deep dive for today. We hope you enjoyed unpacking these pretty amazing developments in AI music generation with us.
Yeah, lots to think about there.
Definitely. Keep learning, keep exploring, and we will catch you on the next deep dive.